Okay, we will be now studying rates of change, and we'll be introducing the idea of derivatives. And so the big idea here, as we're going through this, is that we're going to be studying different types of rates. And really, we'll be studying a rate of change. And the way that we talk about it is we're going to talk about the change of y as x changes. So we need to talk about a rate of change here. So the rate of change of y with respect to x is, you're going to see it written out, change in y. So we're going to talk about a change in y, and we're going to compare that to our change in x. That's the whole idea here. And if you've spent any time in physics, you've seen delta to imply the change. And so that's what we're going to be looking at here. So we're going to have delta y over delta x. Now we can transform this into something a little more familiar to us, especially with our f at a and f at b. So we can even break this down more when we talk about changing y's over changing x's. That should sound a little familiar because it's talking about slope. We're talking about how y changes, so f at b minus f at a over b minus a. And hopefully you see that that is, again, the slope formula. So really, starting out, every time you see derivative or changing y's over changing x's, we need to be relating that to this idea of slope. Okay, and now we're going to talk about average speed. And notice average speed is defined to be the total distance traveled, d. So again, that's coming from here, the total distance traveled divided by the time elapsed. And so graphically, notice that the average speed is the slope of the secant line. So again, here, notice that it's talking about a change in distance over a change in time. When we're looking at our average speed, or an average rate of change, average rate of change, or we'll call it AROC, that's really talking about the slope of our secant line. So graphically, because we need to make sure we can graph these things, if we try to sketch through some kind of graph here, and I'm just going to connect some of these dots, and let's see, we can do maybe something like this. And so we're going to call this our function, and then we're going to pick out some points here. And we're going to call this is going to be point A, and then somewhere over here we're going to call that point B, and then we're going to try to connect those two. And so if I try to connect those, notice that this line is intersecting that graph in more than one place. And so this is going to be our secant line. That's what it's talking about, our secant line. And the slope of this secant line is our average rate of change. Okay, now we have another type of change, and this is called instantaneous speed. It's the speed at a specific instant in time. So that's a little bit different than talking about over an elapsed amount of time, over a long period of time. Here we're talking about as the slope is changing at that one specific point. So in order to do that, that's where calculus is coming in. Now if we talk about instantaneous, we're going to call this our instantaneous rate of change. That's going to be our IROC, and we're going to call that the slope of the tangent line. Now let's look at that graphically. What's going on over here graphically with that then? Well, if we try to mimic the same graph that I just did, which is a terrible picture, but you get the idea. So let's see. I couldn't recreate this if I had to, and I do have to, but I can't. All right, again, we have something like this. Now, instead of picking points A and B, a tangent line only touches the graph in at most one spot. So we could have a tangent line, let's say somewhere here. So maybe at some value down through here of C, then I actually will have a tangent line. And really knowing here, we need to know that slope of that tangent line. That's going to be important for us. Okay, let's look at some examples of this. For example 1, after a person exercises, their rapid heart rate decreases as time passes. So we're going to let H at T represent your heart rate. Write an expression for the rate of change. So there's important. As soon as you see rate of change, you're thinking changing in y's over changing in x's. Now I'm not going to have y's and x's for this problem, but we can figure out which is which. Looking at our context clues, notice that our function is h at t, right? So here that's really going to translate to be changing in h's over a change in t. Okay, so we've got our expression going on here. So it says write an expression for the rate of change of your heart. Oh, now we're going to look from over a period from t equals 0 seconds to t equals 90 seconds after you have stopped exercising. So how would that be represented? Well, wouldn't we need our change from 0 to 90? So I think we would need something like, because here's our function h, so we're going to have h at 90 minus h at 0, and that's all over 90 minus 0. And let's see, what are we going to, we need our rates, and all we have are the seconds there. So we're just going to have units over seconds. So it did not tell us. All right, and that's going to be it, because again, you were talking about an average rate. You're talking about over a long period of time. So here, this would be a good place to know that this is your average rate of change. Okay, so now we're going to have a roller coaster problem, and we are asked to find our, let's see, we're going to find the average speed of the roller coaster from 2 seconds to 8 seconds, and we're given that d at t is going to be modeling the largest drop by this roller coaster. So average speed, keep in mind that's your average rate of change. That's what we're working with. And so we're going to look at d at 8 minus d at 2, and that's all over 8 minus 2. So we would need to get our calculators, and we would get here a close approximation should be 380.82 over 6, and we're going to leave it just like that. You don't have to do a lot of simplifying here, and do keep in mind that our units would be feet per second. Okay, so let's look at our next one, part B. What is the average speed of the roller coaster? So I would stop there. I see the word average speed. That's our average rate of change. And so here from 4 to 6 seconds. So again, we're going to look at d at 6 minus d at 4 all over 6 minus 4. And then that's going to be equal to about, you do my little squiggles because it's approximately 97.02 over 2. And again, our units would be feet per second. Okay, now for part C, and this is where it might seem a little bit tricky, but we're going to get some information and set this up very similar to what we would have done with limits. So we need to estimate the instantaneous rate of change at the speed of the roller coaster at exactly 5 seconds. So notice that we've been finding our average rate of change by having two values, just like we did in our previous two examples. So if we want our instantaneous rate of change at exactly 5, well, we're going to use 5 if possible. And then what about really just fast right past it, like 5.01? And then what about if we get even closer and estimate it at 5 and then maybe 5.001? Then we would get a pretty good idea of what our instantaneous rate of change is. So let's see, let's set up for this first one. So I'm going to have D at 5.01 minus D at 5 over 5.01 minus 5. And then that's going to be equal to 0.4671 over, and that is rounded, so I need to do my squigglies, over 0.01. Hey, now we're going to have to really work this one out because we're trying to estimate. We're trying to see what does this look like it might be approaching. And so we've got 46.714. And what would our units be? Feet per second, isn't it? I forgot what our units were. Right? And we're going to repeat the same process, but we're going to repeat that and use a even closer value. So a closer value, well, that's going to be D at 5.001 minus D at 5 all over 5.001 minus 5. And then that's going to be approximately, if we put all of that in our calculators, then I should get 0.046647, stuff like that, over 0.001. And so it looks like we can probably get a pretty good idea, because from there I'm going to get 46.647 feet per second. And so it looks like we can estimate from these two values here that, and we could repeat this process an infinite amount of times, but it looks like our instantaneous rate of change at t equals 5 seconds, I'm running out of room here, at t equals 5 seconds is going to be, looks like we're going to estimate that around 46, right? Somewhere in between these two. And actually, I would almost choose this one just because we were even closer to 5 than the previous one. Now imagine if we keep repeating this process, we're going to get something pretty close to 46.647 seconds. Or feet per second. Goodness, it is not my knot. So again, feet per second. Okay, with this we will need our graphing calculators, and also we need to make sure they are set in radians. So take a moment and make sure your calculators are set in radians. And now for part A, we're going to have to find f at t for t equals 8. So that means that we're going to have to find f at 8. And so that's going to be 92 plus 5 sine of, well, 8 divided by 2 is 4. And so when you put that in your calculators, you get about 88.216. All right, and so this is really, again, notice that this is a function, and it's talking about, let's see, what is it? Let's see, the model function defined. All right, so it's the traffic flow. So here we're going to have about 88, and that was going to be cars per minute. Okay, so for part B, it says make a sketch of the graph of time versus number of cars and be sure your graph has scale. So this is where we would need to type this in our calculators and make sure we've got all of our intervals and such. So let's go ahead and sketch what we see. I would suggest us starting, let's see, this right here, our amplitude. So at 92, I would think we would need to start at somewhere around 80, and we could go up by maybe 10, so that's going to be 90, and up just a little bit more, let's put that at 100. And just basing off of what I'm seeing here, it looks like we're going to start somewhere like right above there, and then we've got some curve through here, so because this is the sine function. And so let's see, we've got a good graph, I think so. We need a label, so this is going to be, and they give us times t, so that's going to be time, but we need our units, so that's going to be in minutes. And then over on this other side, that's going to be your number of cars, I would expect. Okay, so that's B, and we do have our scale, so that's pretty good. Alright, now let's go through, and the next part C, is asking us to find the average rate of change of the traffic flow over this time interval and indicate our units of measure. So we need average rate of change, and so we're going to have to find F at 15 minus F at 10 over 15 minus 10. And so when we put all that in our calculators, it looks like that's going to give us 9.48462 all over 5. And I would leave that, and it would be cars per minute. There's no need to reduce that all the way down. No need. All right, so let's find the next problem, part D. And so it wants us to calculate, and it looked like we need to set up a few intervals here. So let's see, goodness, we need to estimate. So again, we're estimating the instantaneous rate of change of the traffic flow at time t equals 8. And we're going to do that by finding the average rates of change over these intervals. So notice we're going to have 3 intervals here. The first one we're going to have 8 to 8.1. And so that's going to be F at 8.1 minus F at 8 all over 8.1 minus 8. Okay, and so if we get all that in our calculators, then we're going to have negative 1.586, and that's going to be cars per minute. All right, but they want us to repeat this 3 times so that we've got a good estimation here. So now we're going to look from 8 to 8.01. And so we do need to show this setup, this quotient. That is important for the AP reader to see. The 8.01 minus 8. and that should be approximately negative 1.600 cars per minute. So notice there is a slight change here, but I think we could probably get a good estimate from what we already see. But let's go ahead and finish out the problem. And again, that's going to give me f at 8.001 minus f at 8. All of that's over 8.001 minus 8. And so that's going to be approximately negative 1.6. And that's going to be cars per minute. So it looks like we can pretty much, estimate, do a good estimation that the instantaneous rate of change at t equals 8 is negative 1.6, and make sure we include our units, cars per minute. Right? Now let's look in part E. And part E asks us, why can't the instantaneous rate of change of the traffic flow with respect to time be calculated just using the method in part D? Well, the problem with that, if we just do one number, wouldn't we get something like f at 8 minus f at 8? Oh no, this is disastrous. Over 8 minus 8. And that's going to give us 0 over 0. And remember, we don't know what the crap that is. So be careful there. We're not going to be able to ever use just one value. We've got to find two different points. And again, we're using the idea similar to limits, where we're getting super close to our value. All right, so now we need to find the average rate over the past 2 hours, 2.5 hours, and we're going to use our graph to help us pull in some of this information. So we're starting here, and it looks like our stopping point is way out here. So let's see if we can't find our average rate of change. So we're going to have f at 150 minus f at 0 over 150 minus 0. And that's going to give us f at 150. If we read our graph, that's going to give us 30 minus f at 0 is going to be 0. And that's all over 150. So notice that we're going to get 1/5. And so what's going to be our units? It's going to be miles per minute. All right. So how fast is the car going between 30 and 50 minutes? So between 30 and 50 minutes, how fast is the car going? Well, let's see. That's going to be an average rate of change, isn't it? The average speed between 30 and 50 minutes. So I'm going to look between 30 and 50 minutes. So we're going to have f at 50 minus f at 30 over 50 minus 30. And notice that f at 50 is going to be 20 minus 20. Oh no, all over 20. Well, 20 minus 20 most days, that's going to give us a 0 over 20, which is going to give us 0. So notice here, well, what would be the slope of that line segment there? Well, it would be 0, wouldn't it? So that's kind of interesting there to note. So if they're going 0 miles per minute, if my pen will write, then that tells me that the car is stopped, isn't it? It's not going anywhere. So that's good information to know. Now, when is the car traveling the fastest? So, a couple of ways you could think about when the car's traveling the fastest. Um, the best way I would expect would be looking at the graph. Let's look for some crazy slopes going on. So you might have some crazy slopes. When I say crazy slopes, I mean just some real steep, something going on like this. That's pretty steep. So I would expect, since that looks like it's really more steep than definitely that or that, well, we're probably going pretty darn fast between 0 and 30. So there's one spot, but I would think that we've probably got another time as well. Looking at the graph, it also looks like we might have the same thing going on here. Now, how do I know these two might be the same or they might be different? So I've identified where I think this is going to happen. Now, I need to verify it with doing my slope. So, since we have a graph, remember, slope is rise over run, so we can just count it off. So we're going from 0 over here to 30. So we're going to rise 1, 2, or 10, 20. So we have 20 over, and then we're going to run 1, 2, 3. We're going to run 30. So my slope here is 2/3. Well, let's compare over here at 50. So I'm going to go from 50 to 80. We're looking from here to here now. So again, we need to rise 1, 2. So that's 20 over. How far are we going to run? Well, 1, 2, 3. And notice, well, that was a pretty good estimate. The slope is the same on both of them. So, yay, we've got when the fastest. Oh, when is the car traveling the slowest? Okay, well, let's see. When is the car traveling the slowest? Well, now it's got to be traveling somewhere, so it's tempting to pick those intervals of 0, but I don't think that's going to work because it's not traveling, it's stopped. Need to know, when are we traveling the slowest? Well, looks like it might be out here between 100 and 150, because notice if I talked about slope there, that would be a negative slope. So I would think between 100 and 150. So between 100 this pin, and we said 150. Let's see if we can estimate it, because all we have to do is really count off our slope here. Well, let's see. Instead of rise, we're going to drop. So we're going to drop down 1, right? And then go over 1, 2, 3, 4, 5. So, gosh, negative 1/5. Wow. So that's what that slope, that's kind of interesting there. So I'm going to make a note here that the slope was negative 1/5. Because I have a feeling we're going to see that again. Okay, let's look at our other set of questions. Oh, there it is. It's asking us, well, how fast is the car going? Well, that was our slope. So if we want to estimate that, we said it was negative 1/5. Now, we have to be careful because it's asking how fast. So with speed, that means that we do not want any negative there. Speed does not have a sign associated with it. Just kind of foretelling here. Speed's the absolute value of velocity, so we know it's going to be positive here. And so we saw that the slope was negative 1/5. So if we take the absolute value of negative 1/5, that's going to give me a positive 1/5. And so 1/5, and that's going to be miles per minute. So that's going to give us a pretty good idea of how fast the car would be going. All right, so let's look at F. F asks us a pretty good question. y is the segment between 100 and 150 negative. So y is the segment between 100 and 150 negative, because we're saying you really can't have a negative speed. So try to think about, well, what would have happened there? Well, it's probably because the car turned around, right? It's like it's going back over its path. What is the speed of the car at time t equals 20? So, well, to find that, we probably need to find maybe an average rate there. So at time t equals 20, we could find around that the slope, so f at 30 minus f at 0 over 30 minus 0. And so that's going to give us 20 over 30, which we found earlier, which is going to give us 2/3. Okay, so that's really 2/3 miles per minute. All right, and so at 20 minutes there, well, the speed, now we could change that over if you wanted to and make it miles per hour. Let's see, if we wanted to do that, that's 2/3 miles per minute. So we know that there's 60 minutes in an hour, right? So we're going to cancel here and here, and then we're going to cancel 3 into 60. That's going to leave 20. And so that looks like, and that was 60 minutes per hour. So that's going to give us 40 miles per hour. So for that one, we're going to end up with 40 miles per hour. And we're going to repeat the same process for H. We're looking at 70 minutes. So speed of the car at 70 minutes, we need to do F at 80. Well, it'd be great if I put a 0 there on 80. Minus F at 50 over 80 minus 50. And so that's going to give me 40 minus 20 all over 30. So that's going to give me 2/3 again. And that's going to be miles per minute. And again, if we wanted to convert that over, we would multiply it by 60 miles or 60 minutes in 1 hour. Good gracious. And so that one looks like, again, that's going to be 40 miles per hour. All right, let's see what else we got. Okay, now let's talk about this one. This is interesting because you're really looking at your distance off the ground over the length of time. And so you're waiting in line for 15 minutes. So we've got 5, 10, 15 minutes you're waiting in line. Now your height doesn't change over those 15 minutes. So you're still at the same height you started. Now, it told us it took us 10 minutes to get to the top. So we're at 15. And so, let's see, that's going to be 20, 25. We're going to be at the top. We don't know how far up. We just know we're at the top of the Orlando Eye. And then it's going to take us another 10 minutes to get back down. Now, we have to be careful because we're not going to plow ourselves through the ground. We're going to return and we're going to stay the same distance we were off the ground because we didn't get any taller riding that. So notice how strange that is. That's one weird looking graph, not because I drew it, but because there's no way for us to do what we did earlier when we were saying our F at B minus F at A over B minus A. We had line segments. We had values given to us. With this, we don't have any of that. So this is where we're going to have to come up with some way to determine what's going on and what are our instantaneous rates of change as we continue around that Ferris wheel. All right, so that brings up this next type of problem. And notice they've given us all these different values, and they're asking us to find our average rate of change. Okay, using this table, find the average rate of change, or average speed, between 1.8 and 2.2. So our average rate of change, and we're going to look at, 2.2. Well, at 2.2, we have a function value of 245.76 minus 1.8, which is going to be 232.96, and all of that is over 2.2 minus 1.8. So if we do all of our little algebra magic there, we should get 12.8 over 0.4, which is going to give us 32 feet per second. Wow. Okay, so that's a pretty good idea there. That's pretty sweet. All right, now let's look at the bottom part here. Suppose you wanted to find the speed at exactly 2 seconds. So here we go with this exactly business. So I need to find the speed at exactly 2 seconds. Okay. By using the slope formula and calculating the average speed in a very small increments of x. We can estimate the rate that is close to the speed at the precise moment. So that's what they're wanting us to try. Okay, so we are going to zoom in and get super close. Okay, so that's what's going on this one. They have zoomed in and they're making those really small intervals. And keep in mind that we were wanting to find, hopefully, what's going on over the interval from 1.97 to 2.03. So let's set up our average rate of change, because again, we're going to have to use that in order to find our instantaneous rate of change. So let's read our chart. So at 2.03, I have 240.95 minus 239.03. And again, that's over 2.03 minus 1.97. So that's going to give us 1.92 over 0.06. And so once again, that gives us 32 feet per second.